duality. Tanaka, Klein, Chevalier. I'll explain. So is this familiar to anyone? So this is a classical piece. So the classical Tanakan duality is about is a piece of harmonic analysis. So we probably
I don't know it.
yeah, but
I'm the only one who said he doesn't know it.
No,
No, I also don't know it.
but you probably will cover it in your course. So
Well, maybe after hearing this.
maybe after hearing it. No, but so this is really a classical piece, and it's about compact. The classical Tanakan duality is about compact groups. So I don't want to give all the details, but it is certainly related to the process of complexification that we explained earlier. So in the last talk, I think it was there, we saw that every compact matrix group is the real point of a complex reductive algebraic group.
not compact form.
It is
No,
a compact
this
form.
is
I didn't
general.
prove that it is a compact
Compact
form.
form.
I didn't discuss compact forms.
But I didn't hear the names of Tanaka duality.
Sorry?
I do know what is compact form. But
Okay, so you know what compact form is. So maybe the Tanakan Chevalier duality is the following. Every compact matrix group corresponds canonically and uniquely to a complex reductive algebraic group, and vice versa. And basically we've seen it, but not in a canonical form. So this is what I want to explain now in a very fancy terminology. So we start just by discussing compact groups, and but in fact, the hard part of the theorem, which is surprisingly hard, is to show the direction backwards. That every complex reductive algebraic group has a compact form, and probably so this will not be just word on the board. This will require some argument and understanding of structure theory, and this we will do later on. Okay, but we start with just a fancy thing, and then this is, and again I will be a bit sloppy about everything. Okay. So we start with a group G. A priori, a priori not a compact group, and now I want to explain a certain notion. So rep G will be a finite dimensional complex representation. The category for such. So on this guy we have direct sums and tensor products. Also we have a unit, which is just C itself, a trivial representation, with, well, a trivial representation. And we have a forgetful functor to vector spaces. Okay? So now what I want to consider is the monoid a priori of endomorphism of F. So let me remind what I mean by this. So this is the set of natural transformations F to F. It's become a monoid because they have always the identity and I can compose such. What is a natural transformation? So if I have U in here, so U is a collection, U sub rho maybe, point like this. So so this is for every maybe
X will be better.
sorry?
X will be better.
is a representation rho from G to some GL V. Rho and V are part of the V is hidden here in the notation, and U rho is a map from V to V such that, so U rho is a map from V. This is the guy here. This is rho after forgetting rho itself. This is rho comma V after forgetting rho, right? And if I have another guy, U, coming from, I don't know,
U is a bad
U is a bad guy, right? Bad notation, W, that's better. And so I have theta from G to GLW. This is another representation. So I will have U sub theta. And if I have a function f here, or f, then this should be complete. Okay? So f is, so the U guy is just an endomorphism of each vector space indexed by of the underlying vector space indexed by the representation. And for every f from 0 this is retmorphism or G-morphism I f slash f. Okay, so this is the notion of natural approximation, and I can look at all natural approximations of from this functor to that functor, which is what I described here, and this becomes well, a set with composition, and of course again I have the identity, so this is the monoid. So we denote by Tg the subset of MF consisting of natural transformations commuting or respecting direct sums, tensor products, conjugation, complex conjugation. I'll explain what I mean by this. This is very important. Complex conjugation and assigning and having the U of C is the identity. So a priori here I could have put every scale. It's like normalization. So maybe just a word about complex conjugation. V here is a complex vector space. It does not have a real structure a priori. So I don't have conjugation on V. I have conjugation map from V to another space, which I call V bar, right? So if you take V with the natural C structure, I can think of it as another complex vector space using the conjugated action of C. So this is the same space with another structure. So this over the rings they are isomorphic, but over the complex they are anti-isomorphic, or they are not isomorphic. They are conjugates of each other. Okay, so using this, I claim that there is a natural complex conjugation on every U. So what will be U bar is defined, well, I should explain what U bar does to V. Of course, I should write O here, O V. So this will be an endomorphism of V. So I should explain what it does to X. So O V.
But formally you want it to be an endomorphism of the bar or?
No. So I want it to be an endomorphism of V, a new endomorphism of V. Okay? I'll explain. So X is in V. So I have the element X bar in V bar. I mean, strictly speaking, the same element in the same space, but I think about it differently. So I can look at rho. U is given. U rho V bar of X bar. So this guy, U V bar X bar. So I took X bar, an element of V bar, I applied to it an endomorphism of V bar. So this is some element, a new element in V bar, and I apply bar in it. And I define it to be U bar. So this is a new endomorphism. As it is with tautologies, it's hard to see what it is, but it is trivial. Okay, so
Wait
U.
a second, this is a requirement or is this?
So U in NF is. So I'm explaining this is a requirement for an element in NF to be in TG. In NF,
It's not
you have conjugations, as described above. In TG, I want element U is a conjugation invariant or complex conjugation invariant if U bar is U. Okay, so I want you to observe that there are natural elements in TG that you know. Or let's start by this. There are natural endomorphisms of F that you know. The identity, yes. The identity is a good one. There are others that you do know.
Scalar multiplication.
Scalar multiplication are endomorphisms. This is correct. They will not be in TG though. They will not have this property, unless it's the scalar multiplication by 1, which is identity. So there are others that you do know. If G is not trivial.
Yeah, it's every element algebra. CG.
No, not every element.
No,
is
no,
in.
no.
So there are elements. Okay. I'm asking you basically to give elements from to give endomorphism from V to V,
Which is
which
natural.
when V is known to be a representation space
Central.
of G.
Multiplication by D?
So yeah, the action of some element of G. Every element of G, I can. So maybe I can define UG to be the element which is just taking G here. And so this would be UG rho. This I guess I should write it like that. And UG theta will be theta G. This is an element from W to W. And this will be commuting by the fact that this F here is an intertwiner between these two representations. So we have a natural map which is easily seen to be a homomorphism so let me make another observation, a claim, yes.
But why is UC upper index G is identity on C?
Because C, I guess the notation is leading. C is the trivial representation.
Okay.
So by this, maybe that. I should one. This is not just a vector space. And then the index. Most of the time, I guess I will be using the vector space as an index. This is very wrong, but I can't help it. But there should be.
Thank you.
I mean.
It's not that. It's not that wrong. You can look at it as a G model.
Okay.
And,
I mean, it's like looking at the image here. Oh,
yeah.
okay. Let's not argue about it. I don't know what it is. After all, I'm allowing myself to do it. But don't do it at home. So the claim first is that TG is a group, is naturally a group. So you should, now, I mean, we said that this is a monoid. Again, the identity or the unit of this is the identity endomorphism of his phenotype. Is the guy U that assigns to each V the identity map from V to V. It is all about tautology here. There is no math. Oh, there's only math here. No, only playing with balls. But actually, I could have started with a representation of a monoid, not of a group, and discuss this. But I did start with a representation of a group, so I have some extra structure that makes TG a group as well. So you should explain to me what will be the inverse of a given guy U, or a given collection U sub V. The inverse of, let's write on the board, of U sub V, let's write it as a collection, of course it's wrong to write it as a collection, this is not a set.
Why is it even, you require the U's to be in GL of the, it's not just endomorphism.
No, if you know it's in
Well,
GL,
there are, the U's are endomorphisms.
Not necessarily invertible a priori.
U is a map, if I'm allowed to think of the object of rep G as a set. So it's a map to this. Well,
I have a
it
very
is
simple
a
question. U sub rho, is it it's a linear map from V
yes,
to V?
yes.
Is it assumed to be
It is a
invertible?
linear map. It is a morphism
Yeah, but
in this category.
But is it assumed to be invertible?
No, it is not assumed
Not
to be
assumed.
invertible.
Okay, that's
It is not assumed to be
linear.
invertible. Yes. Okay, sorry.
So
Yeah, it's part of the claim. It will follow from this claim that it will be invertible. So I claim that for every UV there is an inverse, and the inverse, of course, this will require that every such UV is actually invertible as an endomorphism V to V, is in GLV. Okay? And you should come up with the only possible thing. There's nothing about complex conjugation. Now, this is a linear algebra thing that you should tell me. And there is.
But how could we can't do UV inverse because we still
No,
know
you don't know inversion.
we can take the dual of that.
This is the only thing you can do.
But it's not V dual is not V, or do you?
V dual is not V. We have no identification. So we have
So
to every V we can. So if I have U, I have UV. Also I have UV star. This is an endomorphism from V star to V star. So I can abuse it to get an endomorphism from V to V by starring it. So I can take U V star and star it and take this column lying on over all these. Right? So this guy now, right? UV star is a map V star to V star. The star of it will be a map backward. Well, if you want. I'm using the canonical duality here.
So in the requirement of TG, did you you require direct sums from tensor products?
Sorry?
Do you need to require that in TG also?
In TG, I'm requiring to.
Does it make sense? Maybe I'm completely messing it up, but do you need there to require that the map? So you have the dual of when you have a representation, you have a dual representation, right?
You have a counter-gradient representation, what we call, which is the natural transposition of that representation on. So V star here is not just the dual of the. U sub V star is not the dual of the vector space, as my notation might be read if you don't look too hard. This is the counter-gradient representation.
So it's actually U of rho star.
This is rho star V star.
So do you need to require there in the definition of TG that your natural transformations will respect this?
No, it does not respect it. This is a natural operation that I do have on my collection, and I claim this natural operation that I have when G is a group, right? When I construct the counter-gradient representation, is I'm applying star and I'm applying inverse, right?
No, if it respects it, then it's the inverse is the same as
Yes.
It makes sense to. I think it makes sense if my tautology chasing is correct. You can ask. Let me denote instead of U sub V, U sub rho, okay, which makes more sense, right?
Yes.
So you could do U sub rho star or U sub rho star, and you could require both these transformations to be the same. And this is a requirement of your U sub rho collection or running over the object of the replicator.
Though I'm not requiring it.
You're not requiring.
No. Because in a sense, no.
For example, in this example,
It does follow, in a sense. And this is what's behind this claim. It does follow, and this is exactly what makes this guy the, in a sense, and I'm not sure, the inverse of that guy. Okay? And this will follow from the fact that I'm respecting tensor products and this guy here.
now I don't understand.
Okay, we will see. Okay, there is a claim here which I want to prove.
Yeah, but the claim that does not respect the dual function.
No, it does not. I am not
Okay.
saying that
And
it
you
has.
see it in this example. I mean, the image of G in TG, it does not respect it. The dual.
Yes,
Realizing it does not respect.
it does not respect them. Yes. In a sense, there is something which is respected, and this is exactly that statement. This is not what I'm trying to say. And is it clear what Rostar is? The content-gradient representation? Just to remind you, it involves the two anti-involutions or anti-homomorphism. G goes to G inverse, and rho G goes to rho G transpose. Okay, so now I will be down for myself not to get confused, so I'll just follow what I did. And I'm proving the claim. And again, this is a tautology, so I'm wasting your time, but there was this claim at the beginning of this class that I will waste your time. This is
So nice if you're being told.
yeah. Oh, but this is fun. So let's fix these two elements: x in v and y in v star, and let's observe the following. We have the natural map v tensor v star to C, which is x tensor y, which is just applying y to x. And now, of course, we'll apply whatever I have there to this map. So take v tensor v star and the map epsilon. Sorry. So this is a map of representation, of course, by definition. And now I apply here so I'm given this guy. I want to say something about this guy. So I'm using this, so I have u, and I know that this is the same as that, because u respect tensor products. And here I'm writing this again. And this is the identity. Right, so this reads so let's look at this element. This is, I had an element x in V, I apply uv to it, this is another element of V, right? Or maybe, let's do it to y. Just because I wrote it this way. This is an element in V star. This is an element in V. I can apply that. And this is, as we said, this is the evaluation of that element. And by commutativity of this diagram, so this is going.
It's inverse. It should be inverse by orientation. It's the relation of UVX tensor UV star.
The star coordinate comes on the left.
On the right.
On his notation, it's the y comma x.
I wrote once this and what, I guess
You flip it.
x, y, and then leave it here. Leave it down. Everyone happy? Okay, so I took x and y here. I look at, I did the UV tensor UV star to it and evaluated. But this is as just evaluating x and y. This is just e of x times y, as the diagram tells us, which is x comma y. So, what is written here, or maybe let's look at that and let's transpose this operator. So there is this operator, I'm transposing it and applying it to whatever is here, uv. So there is composition here, and now I'm taking x, comma y. This is the same as that, and it is the same as this, x comma y. And this is for every x and every y. So for all x, y, so this means that this operator here is identical. I guess I proved that this guy is left inverse. I leave it to you as an exercise to show that he's the right inverse as well.
So,
This is the way things go with matrices.
so can you explain Rowan somewhat regarding the fact that the star...
I'm not sure, Roman, can you explain it or not?
Yeah, I can explain to Ron. If you can pull the star out of this, if UV star is the same as UV star, then you have UV star star. But UV star star, I mean, we do this identification with the double dual anyway. It's just UV. So the inverse of UV would be UV.
Right.
And I mean, you see it here. In this example, rho G star would be G minus 1. But rho star G is
So it's
not.
actually simply wrong.
It's simply taking an inverse. There is an inversion thing that you should have taken and you didn't, and this is exactly what it says, I guess. Okay, so TG is a group. Let me maybe leave this picture on the wall, on the board, and let me explain how to topologize TG. There are maps, of course, from TG to NVs for every OV in rep, right? This is just taking a look at the V coordinate of this guy U, V here, of the collection UV. And this is some operator space, some GLV, some finite dimensional complex link group, so that there is topology on that.
There are maps from TG to NV.
So yeah, UV goes, UV. U now, like the generic thing, goes to U rho.
You take for each dimensional transformation, you take the map it defines on the specific.
You have a
Representation.
specific V?
Yeah.
Sorry?
For every V.
Specific V?
For a given specific thing, I can just specialize and get. So what I'm saying, there are many maps into actually GLVs, into groups, into Lie groups, and I can take the topology, which is the coarse topology here. Basically, I'm taking the product of all these. This is embedded in the product of such. Only this is not really a product because there is not really a set here, so I'm not using this term, but I'm taking TG is topologized with the coarsest, I think, topology such that these are all continuous. So it's a weak topology. Okay.
do you mean there is no really set?
Sorry?
Why there is no set? Why can't
Well,
you
it is essentially because we have the collection of representation of a given group is a set up to isomorphism, and it's only isomorphism classes that matters, right? So it is a set, but being fancy here, I'm using this language, and Tanaka, yeah, prove if G is compact. This map we described is an isomorphism of the topological group. And later on, Klein came and proved a very similar theorem, a bit more abstract. Essentially, he didn't use this language explicitly, but what he said is that if you consider any category that looks in a certain way as the category of compact groups, the category of representations of the compact group, you have direct sum, you have direct product, you have the trivial representation, you have finitely many, or not finitely many, but you have every element decomposed uniquely into, well, you have the notion of irreducibility, etc., etc., etc. Maybe I don't want to describe it properly. Then, if it looks enough like the representation category of compact groups, then it is such, indeed. There is a spectrum to this representation. So, maybe just a remark. So this was proven before for G abelian. This is exactly, after putting it in the right framework, this is what? On now there's a J.
There's somewhere a J.
I don't know. This programming duality. So you may think of this as some extension of programming duality. So in a sense, the dual object of G is the category of representation of G. And this could be made more precise using the language of quantum groups. Actually. So there is a notion called quantum groups that generalize both the notion of locally compact group and the notion of the category of such, and then you have a complete duality, and this is a subject of, I think, current research. I don't go there now. So I want to give some hints about the proof of this statement before explaining how this is related to complexification. So, are there any questions? And what is the time? And is this too boring?
No?
No? First of all, G compact.
So, what's the goal now? Are you doing
I'm explaining the
the proof of this?
the proof of this statement. And again, I'm not giving all details, and I'm explaining the ideas. And basically, if you want, I mean, there are two words that one should say, and this could be enough. And the words are two names. Peter Weil. I mean, this you should say Peter Weil, and then as an exercise, and Not this time, but but so I give
90% works.
yeah, it works many times. So why should TG be compact? Why do I hit by this map for every V? I hit a compact subgroup here. Sorry.
You can unitarize that.
So I can always unitarize. So G always preserves. I mean, V here is a representation of G. A priori, now it becomes a representation of TG. Actually, this is what I'm saying. That every representation, maybe here you already see some double duality, right? What is written here that you can easily see that this is actually a representation of this group into that representation space of G. This is a double duality thing. And but for G, everything here, G preserves a certain inner product on V, and the claim is that TG will preserve that inner product as well. And why is that? Because I can express this inner product by means of some representation from a tensor product to the complex numbers, as I did a few minutes ago. Right? The only small caveat is that I need to, that this inner product is not actually a complex linear, it's sesquilinear, so in order to make it very formal, I need to use V bar instead of V in one coordinate.
That's where the requirement for the respectness of the bar will come.
Yes, yes, exactly. G preserves an emission in a product. G from V tens of V to C. I want to write it this way. Writing H xy equals G xy bar, H from V tens of V bar to C is equivalent. Of course, and cylinder. And since TG, right, shall I write it down explicitly? Reserves H, so because it respects complex conjugation, as we said, and because it preserves inner product, tensor product, blah blah blah, TG will preserve G. Hence, its image is, I want to say compact. Maybe I didn't say yet, but the image is closed in each of those guys. I guess this is a very easy exercise in definition of this topology. If there is a certain map, TG to GLV, which is not good for a certain vector space, there is a neighborhood of it which is not good, which is not an neighborhood. So it means that basically we hit all these compact spaces.
Can you say the last thing?
Hmm?
Can you say the last thing again?
The last thing, the closeness.
Yes.
I Okay, so what I did prove here is that it's the pre-compactness of the image, and I say that the closeness of the image is an easy exercise, which I explained briefly. Maybe this is why
it did exactly this briefly.
yeah. So again, let's go back here. Assume I have. I'm looking. I have something. I want to show that the image of TG in GLV is closed. Assume I have. Well,
So you're basically showing that the image of TG in the product of the whole GLV is closed.
yeah, exactly. If you want.
And he's saying that being in the image of the TG has to do with coordinate-wise closed conditions, which means satisfying the tensor product, satisfying the. I'm not sure that
It's exactly.
explained.
I mean, I don't want to stay here all the works, but this is something that is easy to understand, and I can do it as much as you could. So, maybe I will not. I will not write down now. I want to explain now the Tanakian theorem. So I want to show that so first of all, I want to claim that this is injective. This map. Okay. So there is a catchy name for this phenomena, that this is injective.
Presentation separate points. We just studied it.
Yeah, so it's representation that's a very point. For every little g here, I can find a representation where it really matters. Which means exactly that this endomorphism that I will get there will not be trivial. So this map is has no kernel. So injectivity coming from here, perhaps separate.
But this is not a general. I mean,
General statement about
compact groups. Okay.
yeah, my groups are compact. I'm assuming throughout from a certain point and on that G is compact. Yes. I mean, this holds for local compact groups.
For irreducible representations, not this finite dimension.
Sorry? Oh, yeah, excuse me. The Van Reykhoff statement says that the unitary representation of locally compact groups separate points. Peter Weil says that the irreducible representations of compact groups are all finite dimensional. So, there are two slogans here coming into the picture. And now, what about surjectivity? So basically this follows from double duality. So I want to explain this, again, very, very briefly, and then we can all have a break. So basically I want a map back, right? Instead of having maybe there is a general statement that I want to put on the board in any case, and this is the following. Find in CG, look at continuous
If G
function.
is finite, this is just the group algebra.
Sorry?
If G is finite, then
Yeah, this is the group algebra. Yes. And you can recognize the group from as an automorphism of the group algebra. In fact, this is what I want to write now. This is not the group algebra yet. This is a categorical monster, but essentially, as we all understand, there's irreducible representations and direct sum of those, a tensor product of those, and there is nothing else. If I just take one copy of each such guy, I can construct everything. And this will be the group algebra. And now we want to come up with a canonical model for this.
T of Tg contains so by the same statement that you wrote here, T of Tg injects into T of Tg.
There is no such.
Tg injects into
T of Tg.
right.
And T of Tg naturally contains G.
It's not an operator.
No, but I could take.
Oh, so sorry. I mean, you should.
Tg is a compact group, so I could take the T of it.
Yes, T of G is a common group. This is the name here. So you can take T of it. This is exactly what I want to do.
And can we somehow see that the T of Tg is
I mean,
contained
just
in G or something?
this is what we will do. We will use the fact that the T of G is a compact group, but I just want to make a remark. This is already W,
This is already
right? The first dual is something else. It's not a group. It's the representation category or the group algebra, which basically I started to write down now. So in C of G, there is a nice subalgebra. The subalgebra generated by matrix coefficients of finite dimensional representation. Maybe let's call it OG in CG. Equivalently, OG is the collection of elements in CG, of functions that span a finite dimensional, or are contained in a finite dimensional sub-representation of CG. Think about CG as a G space. G act on it by the left regular action. So this is a representation, infinite dimensional representation of G. And there is a dense someone should again shout two names for explain why it's dense. There is Stone Bashas. There is a dense subalgebra contains of elements which are each of them is contained or generate a finite dimensional subalgebra. And so this is some algebraic part inside here. And OG, we know again. So I'm not explaining everything, right? But I'm counting on the fact that you know what is going on. So from your harmonic analysis classes that we will give soon. So this is. I could have made a choice of this is G dual. This is the collection or set of isomorphism class of irreducible representation of G.
It's usually denoted hat or check.
If I could have just looked at this ring arbitrarily, I pick a representative of each irreducible representation. I'm looking at it. You should think of this as a multiplicity. These notations become very natural if I do think of CG not as a representation of G, but as a representation of G times G for left and right action. actions simultaneously. If I just think of it as a representation of G, then it acts on V lambda, G, and this is just some multiplicity of it, but it's exactly of the same dimension. This is the part of the general theory, and we have this decomposition of this space. This. So what is that I want to say? Oh, so I guess that I want to explain, or maybe another way to think of it is the sum of ends. And again, we have G times G, action on this, action, we have precomposition and postcomposition. And there is a natural map, I want to say, from end F.
It's 27, just for
Okay, so maybe I'll write this on the board and we think about it, and I thought I will finish this in 20 minutes, but OG. So maybe I'll just explain this and we think about it over lunch. Every endomorphism of the factor F, of course, give us endomorphism of each irreducible representation. It's just looking partially on things. And whenever I have endomorphism of each irreducible representation, I can construct by it endomorphism of each representation whatsoever. Clearly. And so this is an isomorphism, and somehow I want
But
to
this is direct sum is
look at TG in here and to explain what it is over there. Sorry?
so direct sum is finite sums or
I mean, each of these is a finite sum, is d lambda squared.
no, my question is when you write direct sum of infinitely many vector spaces.
Because this is an algebraic piece. This is just algebraic direct sum, and this is the dense sum algebra of this binary algebra here.
When you give me an element in end F, not it could have infinitely many non-trivial endomorphisms, right?
Yes.
Hence it would
It's certainly yeah, so in particular, but for each lambda it will give an endomorphism of V lambda.
right. But my question is regarding it's my lack of knowledge of what is a direct sum. Direct sum is infinite sums or finite sums?
Direct sum, the direct sum is finite combination, that for each element here.
But almost surely your coefficient is 0, right?
Yes.
Only it's supported on a finite chunk of the sum. And
Oh,
there it's
Yeah,
supported
yeah,
on
no, what I did write is not correct. Yeah, thanks. I wrote a bad. There was no reason.
It didn't
Thank you. Yeah. Okay, let's make a stop here and after lunch.